We're going to run through the Zero Trust Exchange architecture in detail, looking at other functionality that's available, and the API infrastructure. If you think about how Zscaler managed to scale this, we've separated out the different functions that invariably exist in an on-premises architecture. We have the control plane. The control plane is where all of the policy administration and functions are done there. All of the authentication exists at the control plane, and all of this is highly resilient, available across multiple data centers. But by splitting out the control plane from the enforcement plane where the users connect to, those are the Zero Trust Exchange points, we're able to scale that massively. And the policy enforcement are the scanning engines that apply that policy. It means that a user can connect, they can authenticate at the control plane level, they get their identity token, and then they connect to the public service edge or the brokers for these connectivities. The public service edge understands the security token that is presented to it from this user that's connecting, and will talk to the control plane and say, what policy should I apply for this transaction? And it caches that policy construct. At a point in time, the policy engine doesn't know anything about the user or the device, but it does know what policy to apply to that transaction. Every transaction is then logged against that security identifier, and then we transmit those logs to the logging plane periodically. And the logs are inherently encrypted. The obfuscated include the user information, the URL information, and we highly compress those logs. By splitting out the control plane, the enforcement plane, and the logging plane, we're able to massively scale this multi-tiered architecture, meaning that a user's policy can follow them around the globe. The policy is very small, so any changes are updated immediately, and the logs are inherently encrypted and obfuscated because of the way that we log the transaction against the security identifier, which is a transient token across all of the nodes. Of course, we also have API integration so that we can do automation. That means you connect to the control plane for those APIs. And then there's API in the sense of the log streaming those logs from the logging clusters into your SIMSOC solution. The central authority is the brains of understanding the public service edges, the health of those nodes, the availability of those nodes, and the scaling of those nodes. The central authority returns information about which node the user should connect to in terms of that pack file configuration and the DNS resolution functions that happen there. The central authority is the brains of the Zscaler private access cloud as well, in terms of understanding your applications that you define from your application segments, which app connectors are able to service those requests, the health of those app connectors, and the paths that the user should take to get to those applications through those app connectors. And it manages the visibility of those applications and gives you real-time updates of those applications. And it retrieves the ZDX, the digital experience monitors, and the probes from the client, and works with a data lake to give you that invariable visibility of all of the applications that you have those probes for, and manages that content over time. How does the central authority work? Well, the central authority is the brain. An administrator will log into the admin interface. They get a security token to access the data. There's role-based access control for that administrator to control what they're able to see, and those role-based administrations might say the user is able to see the user information in the logs, not allowed to see the user information in the logs, as well as not able to see the logs at all, as well as having policies for, is this administrator of a certain rank able to manage certain security policies, URL filtering policies, firewall policies, and those your admin ranks. When it comes to the logs, the administrator will be granted or not granted a token that enables them to access the logs, and if they have the right token, to be able to decrypt the logs. So the logs are stored and indexed with a security token, and only an administrator with that security token is able to download the logs and then decrypt the user information from those logs. The logs are secure, and then you could also have a four eyes principle where an auditor is the one that is able to decrypt those logs. When we think about the policy construct, any policy object that is applied in the administration interface is essentially a delta from the previous configuration. An object which applies to a user or a group of users or a location is a very small bitmap of references towards a policy construct. When a user connects to a public service edge and the node sees that security identifier of the user, it needs to pull down the policy for that user to apply the policy. And that policy could be very large if we were to store it as a list of all of the policy objects. But the policy that differs for user A versus user B from company 1 from company 2 are very similar. Using the kind of WAN optimization techniques, you only need to store a base object. And then we only transfer the differences from that base object or from the last object when things have changed. So only policy changes are sent to those nodes. We do that very quickly. And the bitmap 192 bits. And then there are changes in references from that policy bitmap. This means that the scale of the cloud can continue to increase, as well as those downloads of those policy objects are very short because we're transferring very minute pieces of information. This is also true of the traffic inspection. If you think about a legacy environment, where a packet comes into a proxy, there's a URL database, it's got to do a lookup, it's got to hand off to an antivirus engine, it's then got to decide to send that to a sandbox, and then a data loss prevention engine, an IPS engine, a firewall engine. All of these things are breaks in the TCP connections. They're breaks in terms of the flow. Every single one of these breaks means that a session state needs to be held, which adds delay, adds latency to the lookups, and means that there are scalability problems for each of these boxes that all need to pass through the proxy that's handling those transactions and the handoffs. The public service edge has single scan multi-action, meaning that a packet comes into a public service edge. We will strip the IP header, we'll hand it off to all of our different engines in memory, and be efficient in terms of when those breaks occur, in terms of deciding to block based on the first one to respond, meaning that our public service edges can scale massively because they're all able to apply the same policy. They're all doing the same processing, apart from the need to hand off to a sandbox, which is an out-of-path decision because a file has to be exploded in the sandbox. But we can be efficient in terms of those policy decisions. In terms of the public service edges, the data centers that Zscaler operates, we have an open peering policy. We peer with cloud service providers, so Google, AWS, Microsoft, Akamai is the world, to give very fast transit one hop away from those service platforms. We also have global peering with transit providers, GTT, Zayo, Telstra, all of the global transit providers with indirect peering and through IX peering. And then we peer with the customer content providers, your local ISPs, Orange, BT, Verizons of the world, so that a user has fast connectivity into our nodes. And then from our nodes, we have fast connectivity into the applications that a user needs to access through invariably milliseconds away from the users and from the applications those users need to access. We have an open peering policy. You can connect, you can request access to peer with us.